So in Module 3, we're going to go ahead and take a look at some polynomials. And to start off in Section 1, we want to look at the basics of a polynomial function, some definitions, and some characteristics of polynomials. So we start with the definition of a polynomial function, and that would be a function involving only non-negative integer powers of x. So what this means is if I have a polynomial, all of the powers have to be positive. So for example, if I look at 5x squared minus 3x plus x cubed minus 3, this is a polynomial that only has positive exponents, so it is a polynomial function. On the other hand, if I look at 3x to the negative 2, my variable has a negative power, which means it is not a polynomial. And if I look at 3 square root x plus x squared, even though x squared has a positive exponent, roots technically would be fractional exponents, which are not integers, since integers only involve whole numbers, which means it would also be an example of a non-function, a non-polynomial. It is not a polynomial. Next, we want to look at the degree of a polynomial function. So the degree of a polynomial function comes from the term with the highest degree. So each term can have its own degree, but the degree of the entire polynomial is the biggest one. So if I'm looking at an example, such as 3x squared minus 6x to the 5th plus 7, the degree comes from the term with the biggest exponent. So it's not necessarily the first term. If I look here, my second term has a degree of 5, whereas my first term only has a degree of 2, and 5 is bigger than 2. So the degree of the entire polynomial is going to be 5. We can also look at something called the leading coefficient, which always goes with the term with the greatest degree. And the leading coefficient is always just the coefficient of the term with the greatest degree. So in this case, I look at the entire term, negative 6x to the 5th. So the leading coefficient would be negative 6. So next we're going to talk about the graph of a polynomial function. And we're going to talk more about what the graph can tell us later, but for right now, what the graph of a polynomial function is going to tell us is if the polynomial is even or odd degree. So it can tell you if a polynomial function is even or odd degree. And as I stated, we'll eventually be able to tell more about a polynomial function, but one of the biggest things it can tell us is the degree of the overall polynomial. So looking at these first sets of examples, we want to know which of the following are polynomial functions, and if it is, what its degree is. So remember, in order for a function to be a polynomial, every term has to have positive integer degrees. So we look at our first example, we have f of x equals 7 minus 3x to the 5th. 7 has a degree of 0, x to the negative 3x to the 5th has a degree of 5, which means this is a polynomial function, and its degree is going to be 5. Next, we look at the function f of x equals the cube root of 2x. And as I previously stated, roots are fractional exponents. It doesn't matter which root you're taking, whether it's a square root, a cube root, a fourth root. Anytime you're taking a root, it is always going to be a fractional exponent, which is not an integer, which means this is not a polynomial function. Next we have g of x equals x squared minus 1 all over x cubed minus 4. Now while x squared and x cubed are positive whole number exponents, if I have a rational function such as g of x, anytime a variable appears in the denominator, if I would write it out as a single function, it would actually be a negative degree, which would not be positive, which means this next example is also not a polynomial function. And lastly, we're looking at g of x equals 8x squared times x to the 4th plus 3. So it's going to be easier to look at it once we distribute the 8x squared. So we get g of x equals 8x to the 6th plus 24x squared. So now that we're looking at our polynomial, both of my terms have positive exponents, which means this is a polynomial function, and its degree is the greatest exponent, which is 6. So next we want to take a look at power functions, since most polynomials can be compared to their basic power function. The degree would be, the term with the highest degree would be its power function that it is based off. So a power function is a function of the form f of x equals x to the n, where n is a positive integer. So if we look at several functions here that we may have seen in the past, we have f of x equals x squared, f of x equals x cubed, and then f of x equals x to the 4th and f of x equals x to the 5th. So we want to go ahead and take a look at these power functions and see if we can notice anything about them. If I look at the x squared and x to the 4th graphs, they both look like they follow the same shape, and both of their ends tend to go in the same direction. And if I look at the f of x equals x cubed and x to the 5th graphs, they also look to follow the same type of graph, and their ends go in opposite directions. So I can boil this down to the even functions. Their ends go in the same direction, either both up, or we could have it so that they're both going down. And our odd functions, their ends go in opposite directions. So one is going up, one is going down. And it doesn't matter which one starts out, because we know that it's going to continue going in the same directions once you start. So now we're going to take a look at the zeros of a polynomial function. So when we talk about what the zeros or roots of a polynomial are, those are the values of x such that f of x equals 0. So any value of x that you plug in that gives you 0 as a value for y. So another piece of information we know is that the degree of a polynomial tells you the max number of zeros a polynomial has. So for example, if I have a degree 5 polynomial, I know it has at most 5 zeros. Now, some of these zeros may be real, some of them may be complex, which is what we're going to talk about next. They could all be real, they could, or most of them could be complex, which is what we're going to talk about now. Next is how to determine if you have real zeros or complex zeros. So if you want to know the number of real zeros of a polynomial, what we're going to do is it depends on if it's an even or an odd degree polynomial. So let's first talk about an even degree polynomial. If you have something that is an even degree and you want to know how many real zeros it has, it's based on, it's either going to have 0 or an even number of real zeros. And that comes from, if you were to look at a graph, an even degree function can only cross the x-axis an even number of times or none at all. So for example, if I'm looking at x to the 4th minus x squared plus 1 as a polynomial, its degree is 4. So the possible number of real zeros it can have is 0 or every even number up to the degree, which are 2 and 4. So it either has 0, 2, or 4 real zeros. And without graphing it, we won't know for sure which of those it has. Next, we want to talk about something that's an odd degree. Well, if an even degree function has an even number of real zeros, an odd degree function has an odd number of real zeros. And it can't have 0. It has to have at least 1. So if we're going to look at an example here, so if we look at, for example, x cubed minus 1, the number of real zeros has to be every odd number up to the degree, which in this case is 3. So it has 1 or 3 real zeros, and so those are the only odd numbers up to 3. To know for certain the number of real zeros a polynomial has, you're going to want to look at its graph. And when you're looking at the graph of a polynomial, whether it's even or odd degree, the way you determine the number of real zeros is based on the number of times the graph crosses the x-axis. Also known as just finding the x-intercepts. So the x-intercepts of a graph are always going to be the number of real zeros. Lastly, we're going to talk about complex zeros of a polynomial. So if you remember back, the number of zeros a polynomial has is the degree. So if I have a degree 5, it has 5 zeros, some of which can be real, some of which may not. So in order to know how many are complex, you have to take into account the degree and the number of real zeros. So based on the degree of the polynomial and the graph, you can determine the number of complex zeros. So let's take a look at an example. So suppose I have a degree 5 polynomial. And let's say its graph looks like this. I want to know how many complex zeros it has. So let's determine the number of real zeros it has. So every time it crosses the x-axis is a real zero, which it has 3 real zeros. The number of zeros adds up to the degree, which is 5. So in order to get from 3 to 5, you add 2, which means there are 2 complex zeros. And when I add 3 and 2, I get 5, the degree of the polynomial. It could work for any degree. If I had a degree 6 that crossed twice, then I would know there were 4 complex zeros. There always has to be an even number of complex zeros. So there's always an even or 0 number of complex zeros. And we're going to talk about why a little bit later. So let's go ahead and combine everything we've talked about so far with a couple things from Module 2 to take a look at some graphs. So for each graph, we want to know the degree of the polynomial, whether it's even or odd, the number of real zeros, any intercepts, which would be x and y, and any maxes or mins. So the reason why when we talk about the degree of the polynomial, we're only talking about even or odd is because some of the zeros could be complex. So we don't actually know if the number of real zeros equals the number of zeros. So looking at our first example here, the ends of my graph are going in opposite directions, which means this is an odd degree. Next, we want to look at the number of real zeros. So that's the number of times it crosses the x-axis. And if I look, there are 3. So there are 3 real zeros. Next, we want to look at any intercepts. So this is x-intercepts and any y-intercepts. So if we look, the x-intercepts are the same as the zeros. So those would be the point 0, 0, 2, 0, and 3, 0. And then we want to look for the y-intercept. It also happens to be the point 0, 0, so we're not going to list it twice. Then lastly, we want to look at any maxes or mins. So I feel like we have 2 turning points on our graph. And a turning point either represents a max or a min. So the first turning point we have at 0.785, 2.113 is going to be a max. So max at 0.785, 2.113. And then our second turning point, 2.549, negative 0.631, is going to be a min. So we have a min at 2.549, negative 0.631. Our next example. So first we're going to look at the degree, and the ends of the graph are both going down in the same direction, which means it is an even degree polynomial. Next, we want to take a look at the number of real zeros. So count the number of times it crosses the x-axis, and we are going to get 3. Now, we talked about the fact that even degree polynomials have to have either 0 or an even number of real zeros, but I only counted 3 real zeros. And that comes from this third real zero. It's because that 0 sits on the x-axis, it has what's called multiplicity 2, which means it counts as a real 0 twice. So we can really think of this as 4 real zeros. But we only count it once when we're listing it as one of our intercepts. So when we list our zeros, we're going to have -2, 0 as one of them. We have -1, 0. And we have the 0.10, which we're not going to list twice, even though it has multiplicity 2. And then we also want to list the y-intercept, which is going to be down here at 0, -2. And lastly, we want to look at any maxes or mins, so any turning points. So we have 1, 2, 3 turning points in this graph, 2 of which are maxes. So we have a max at -1.6, 1.6. I'm only going to write 1 decimal place for this one. And then our second max is at 1, 0. And then we also have a min, which is at -0.2, -2.1. And you can put all 3 decimal places if you would like, or 2, as long as you have at least 1 decimal place. So the last thing we're going to look at to tie it all together is end behavior. When we talk about end behavior, it describes the trend of the graph as x approaches positive and negative infinity. And the way that we write that, so the way we write the statement x approaches positive and negative infinity is to say x, and then we draw an arrow, and then we count positive or negative infinity. So very last graph we're going to look at, and we're going to tie everything we've talked about so far in section 1 along with some of those other concepts from module 2, and look at the polynomial f of x equals x to the 4th plus 6x cubed plus 5x squared. You are going to want to, if you haven't already done so, pull up a picture of that on Desmos to go ahead and take a look at, which is what I'm going to include here in a second. So if you look here, this is what the graph looks like in Desmos. So the first thing we want to know is what the degree of the polynomial is. Now, because we have the equation, not only do we know if it's even or odd, but we also know what the actual degree is. So we look, our greatest exponent is 4. So it is going to be a degree 4, which makes it an even polynomial. So next we want to know what the x and y intercepts are. So if we look on our graph, we have 1, 2, 3 x-intercepts, one of which also counts as the y-intercept. So those points are at -5, 0, -1, 0, and 0, 0. Next, we want to look at the domain and range of the function. So remember back to module 1 when we talked about domain of some of our parent functions, a power function, every single one has the same domain, which is all real numbers. So we can write the domain of our function as -infinity to infinity. Now, because even degree functions have a high or a low point, the range is not always -infinity to infinity. We want to look at the lowest point possible on our graph here to figure out the smallest possible value in the range. And that's going to come from this point down here. So if I look, the smallest possible y value I can get out is -48.581. So that's going to be the smallest value in my range. So -48.581. But there's no max point I can get. Max value I can get, I should say. So that it's going to go until infinity. So smallest value, -48.581. largest value, no idea, since both ends go off towards the positive direction. So next we want to find all local max and min. So we want to find our turning points. So we've already labeled one of them. And then we have a second one up here, and we actually have a third one at the point 0, 0. So only one of these turning points is a max. So we have a max at negative 0.6, 0.6. And then our other two turning points are both mins. So we have mins at negative 3.85, negative 48.58, and at 0, 0. Next, we want to know when the function is increasing or decreasing. So that also goes along with turning points. So if we draw our arrows, we start decreasing, then we increase, then we decrease, and then we increase again. So off to the side here, I'm going to write our intervals. So increasing. So we increase from negative 3.85 to negative 0.65. Because remember, for intervals of increasing and decreasing, we always use x values. And then union, since we have a second interval, we then increase from 0 to infinity. Next, we want to look at our intervals of decreasing. So our graph starts decreasing, so from negative infinity to negative 3.85. And then union, since we have a second interval of decreasing, between negative 0.65 and 0. Lastly, I want to discuss the end behavior of the graph as x approaches positive and negative infinity. So I'm going to do that off to the left here. There's a couple different ways you can write end behavior. You can say what the function is doing and then describe x, or you can put what x is doing first, then describe the end. But because this is an even polynomial, the end behavior for both positive and negative infinity is going to be the same. So if I were to zoom out on this graph to look at the ends, as x is approaching positive infinity, or getting more and more positive, the end of my graph is also doing the same thing, which means the function f of x is approaching positive infinity as x approaches positive infinity. And then if I were to look at my function as x approaches negative infinity, the graph is still becoming more positive, which means my function f of x is approaching positive infinity as x approaches negative infinity. And all of this information ties in to give us G, which is a sketch of our graph of f of x, which you can get from Desmos.